Alright, in this video, I'm going to cover section 15.8, which is about triple integral in spherical coordinates. This section is going to be divided into two videos, and this is the first one of them. So in the previous section, we did triple integrals in cylindrical coordinates. And in this section, we're going to introduce another coordinate system called spherical coordinates. So the idea is this. Suppose you have a XYZ space as usual. Z space. And then the idea of coordinate system is basically to give an address to each point. And then the simplest way of giving an address is to assign three numbers, x, y, z, corresponding to the distance from the origin to each coordinate axis. That's, so to speak, the x, y, z coordinate system. Then now, here's another way of doing this. Let's project this down on the xy plane. So this point is xy 0. Then now, to give an address to this point here, first let's use the distance from the origin to this point. And let's call the distance a rho. And then let's call the angle from the z-axis to this line segment. So this angle, phi. This is the Greek alphabet rho, and this is Greek phi. And then also we know that we have the polar coordinates for the xy, and then this angle is called theta. And then the distance from the origin to this point is called r. And then we can describe this point, the coordinates of this point, using those four numbers. However, we only need only three numbers, but let me just write down. So by using polar coordinates, x is written as r cosine theta, and y is equal to r sine theta. That's fine. And then now also z is actually written as rho cosine phi. Why is that so? So z is this height, right? And then indeed, if you look at this picture, by cutting everything by the plane going through here, plane like this, going through z-axis and this line segment, and then what you see is something like this. Here, z-axis, and then this line here, this axis is like the axis going this way, okay, going through this. And then we have a point xyz here. And then this is right angle. And then the length of this line segment is rho. And the angle from the z-axis is phi. And then, what's the z-coordinates here by using rho and phi? Or z-coordinate is height here. Oops. That's the height here. But that's the same as looking at, so this angle is phi. So by pretty much the definition of cosine, you will see that the length here is rho cosine phi. Or you may think this way. So that means here, this angle is pi over 2 minus phi. And then you can just look at the height is rho. Yes, the height is, here height is rho cosine phi, or that's rho sine pi over 2 minus phi, whichever. So in either case, you'll see that the height z is rho cosine phi. Then now we have four variables, four numbers like theta, r, rho, phi. But we only need three because everything in 3 dimensions, so you need only 3 numbers for the address. And for that, you have to express r by using the other numbers. So this is r, right? Here's r. Remember, this axis, horizontal axis here, is this axis here. So r, now what's r here? R is, by looking at this picture, rho cosine pi over 2 minus phi, and then that's rho sine phi. So therefore, r is rho sine phi, so you can just plug in this here and here, and then you get x is r cosine theta, but r is rho sine phi cosine theta, and y is equal to rho sine phi sine theta, and then z is rho cosine phi. So those are called spherical coordinates. So they're called the spherical coordinates. Well, strictly speaking, spherical coordinates are rho, theta, phi. So that's what the spherical, those are the spherical coordinates. And those are the formulas that relate xyz coordinates with the spherical coordinates, to be precise. But then now, here, one thing I should mention is that rho is the distance from the origin to the point. So it's a distance, so it can never be negative. So rho is between 0, and it could be infinity. It could go forever. Or cannot be infinity, but it could go forever. So rho is from 0 to infinity. And the theta is the angle on the xy plane, so you can just go around once. So theta can take from 0 to 2 pi. Then now, how about the phi? Actually, in order to cover all the points on the xyz space just once, we need only up to pi for phi instead of 2 pi. The reason is because here, the reason we need only pi is because, let me just write it down here. For example, suppose you have xyz space like this, and then so phi is the angle from the z-axis, so you can just go around the phi like this. And if you go above pi for phi, you just go around like this. Okay, but suppose you have a point here whose xy coordinates are negative 1, 0, 0. Suppose you look at the point negative 1, 0, 0 on the x-axis. And then here, this point, so xyz is negative 1, 0, 0. This point corresponds to, in terms of rho theta phi coordinates, is what? Well, negative 1. So rho is 1. Rho cannot be negative. Rho is 1. And then theta is the angle from the x-axis on the xy plane. So theta is pi. And then phi, the only thing you need for phi is to get to the x-axis from the z-axis. So phi can be only pi over 2. Okay. Then now, but if we allow phi to be bigger than pi, we could also have 103 pi over 2. So 3 pi over 2 is like going to all the way up to the bottom and then come back to this here. And then this way, if we allow oops. This is phi is equal to 3 pi over 2. So if we allow phi to be bigger than pi, we double count this. We would double count this point in those two ways, which is not good. We just need only phi and theta, so that we just need to cover all the points only once. Just to, we wanna count each point only once by using these spherical coordinates. So that's why we need only up to pi for phi. Okay, and also I should mention that in terms of spherical coordinates, since rho is the distance from the origin to the point, we always have x squared plus y squared plus z squared equal to rho squared. Well, you could actually verify this by directly plugging in those. Like here, x squared is rho sine phi cosine theta squared plus y is rho sine phi sine theta squared plus z is rho cosine phi squared. And if you simplify this, this is written as rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta plus rho squared cosine squared phi. Okay, and then you can just factor out those. And then you get rho squared sine squared phi cosine squared theta plus sine squared theta plus rho squared cosine squared phi. And the sine cosine squared plus sine squared is equal to 1. So this is just rho squared sine squared phi plus rho squared cosine squared phi. And then by factoring out rho squared, you see sine squared plus cosine squared, and that's equal to rho squared. So you could actually directly verify this. But in any case, so this is just closing parentheses. In any case, you may consider this as part of the formulas for the spherical coordinates. Okay, then now to get used to the spherical coordinates more, let's do this exercise. Describe the surface defined by rho is equal to 3. All right, so here's the answer. How do you do this? Rho is equal to 3 is by using the set notation. You have to get used to the set notation. But in terms of set notation, with rho theta phi coordinates, this is the set of all points rho theta phi such that rho is 3. Okay. But it's that, well, rho is the distance from the origin to the point, and this is a set of all points so that the distance from the origin is 3. So this is nothing but, more in a plain language, this is a sphere with radius 3. Sphere with radius 3. And indeed, we have x squared plus y squared plus z squared is rho squared. Okay, that's part of the formulas for the polar spherical coordinates here. And then, but that's equal to 3 squared, and this is nothing but the sphere with radius 3 with center the origin. The sphere, the surface of the sphere with radius 3. Okay. Then that's the spherical coordinates, but let me just mention one little thing before moving on to triple integrals. Let me note. Sometimes, depending on the textbook, depending on the subject, sometimes phi is taken from the xy plane instead of the y-axis. Namely, this is our point, xyz. So we do this way, phi is taken in this way, but depending on the textbook, so this is our r, and this is xy0. Depending on the textbook, phi is taken in this way from the x-axis. Well, from xyz, I'm sorry, from the xy plane, this way. Like maybe in physics or mechanics or some other branch of mathematics or branch of some other branch, some other subject which uses a three-dimensional coordinate system. Sometimes they use phi in this way, so be careful. So in this case, of course, r is equal to rho. So in this case, r is equal to rho cosine phi instead of sine phi. And then, so that means x is written as rho cosine phi, cosine theta. Y is equal to rho cosine phi, sine theta. And then z is equal to rho sine phi. So if you take phi in this way, phi is from negative pi over 2 to pi over 2 instead of 0 to pi. So be careful if you take another class that uses spherical coordinates, which convention is used. Which one to choose is completely conventional. But in this course, we're going to stick to this convention, this way. We're going to take phi from the x-axis. Okay, now then, using the spherical coordinates, we can do triple integrals like this one. Here's an example. Evaluate triple integral e to the power of x squared plus y squared plus z squared 3/2 dv, where E is the set of all the points x, y, z, such that, maybe let me just put it here, such that x squared plus y squared plus z squared is less than 1. So this one is, if you have an equality instead of inequality, this is just a sphere with radius 1, and we have here an inequality, so that means it's a solid sphere with radius 1. Then now, for triple integral problem, if you see an expression like x squared plus y squared plus z squared, that's the indication that you should use a spherical coordinates. If you see only x squared plus y squared, okay, without z squared, if you see an expression like this, that's the indication that you should use polar coordinates. Okay. But if you see x squared plus y squared plus z squared, that's the indication that you should use spherical coordinates. Anyhow, so this one is, of course, an exercise for spherical coordinates. So here's the answer. So let's use spherical coordinates. Use these spherical coordinates. Spherical coordinates. And then, by the spherical coordinates, x squared plus y squared plus z squared is equal to rho squared. That's part of the spherical coordinates formula. And then, of course, x, y, z are expressed in this way. However, for this problem, we don't need it because the idea is to express everything using spherical coordinates without using x, y, z. And then this becomes just rho squared. And then, of course, our solid E is what? It's everything inside radius 1, sphere with radius 1. So E, in terms of rho, theta, phi coordinates, in terms of spherical coordinates, this means rho is between 0 and 1. And then you go through all the spherical coordinates. So theta is between 0 and 2 pi. And then phi is between 0 and pi. Okay, be careful. Phi is always at most pi. So, is that all? Well, essentially what you have to do is just plug in those data to here. However, just like the polar coordinates or cylindrical coordinates, dv is not just d rho, d theta, d phi, but rather here, dv is dx, dy, dz in terms of xyz coordinates. But this is written as, now this time, this is rho squared sine phi d rho d theta d phi. Okay. I'll explain this later after this problem. So to be explained. For now, just believe this. To be explained. And let's just finish this up. So remember for cylindrical coordinates, dv is r, dr, d theta, dz. That's cylindrical coordinates. Cylindrical coordinates. So we need extra I here. Well, for polar coordinates, just this, right? But for the spherical coordinates, we need this as our extra factor. And then, like I said, I'll explain the rationale for this later. But for now, let's just solve the problem. So all we have to do is just plug in those, and those to here. So therefore, the given integral is written as, so given integral, that's e to the power of x squared plus y squared 3/2 dv. This is written as triple integral, so we have 3 limits, e to the power of rho squared 3/2 times rho squared sine phi d rho d theta d phi. And then the limits are rho is between 0 and 1. And then theta is between 0 and 2 pi. And phi is between 0 and pi. Okay. So all we have to do is just work this out. And this is simplified as 0 pi, 0 2 pi, and 0 1. And then rho squared e to the power of rho cubed times sine phi d rho, d rho, d phi, d rho, d theta, d phi. Phi. Okay. And then once you get to this, everything is just mechanical. You just work out the innermost integral. For this, actually, strictly speaking, you have to use U substitution. Well, if we are used to it, if you once get used to this, you can just do like this, times sine phi rho is equal to 0, rho is equal to 1, d theta, d phi. Okay, and then this is equal to 0 pi. And then you plug in, you get 0, 2 pi, 1/3, e minus 1, sine phi, and then d theta, d phi. And if you work this out, I'm not going to do the details here, you are supposed to get 4/3 pi e minus 1. That's what you're supposed to get. Okay, then now, so that's the end of the problem. But now let me explain why we have this dv, which is dx dy dz, is equal to d rho d theta d phi together with this guy, this factor, rho squared sine phi. So let me just briefly explain. Why we have this. Sine phi d rho d theta d phi. So let me give you the explanation. So here's a picture. Basically, this dv has to be the increase in the volume with a small increase for rho theta phi. And then here's a typical picture. Suppose this is our x and y. And if you increase phi a little bit, so this is the increase in phi. This point gets bumped to here downstairs. And also if you increase rho is here, distance from here. So rho, if you increase rho a little bit, increase in rho is this. So this is d rho. And then if you increase theta a little bit, increase in theta gives you another direction, like this. Like this. And then this is the volume dv. The volume of this little thing is dv. Then now, if you project this down on the xy plane, what you see is, oops. Like this one. And then we have some increase here. And the increase of this angle is d theta. And here, the distance here, so we see is what? Well, let's see. So this is a picture you see downstairs. And then now, let's magnify this portion. Like this. And then the question is just compute the volume of this in terms of d rho and d theta d phi. And then the length of this line segment is d rho. And then we're gonna approximate this as a cube, or actually a three-dimensional rectangular box. So what we need is to this times this, okay? So 3 line segments. And then here, first of all here, the length of this line segment corresponds to here. And that is by pretty much definition of the radian. This is rho times this line segment here is rho times d phi. Okay, because the angle here is d phi, right? So the angle times the radius is the arc length here. That's pretty much by definition of radian, actually. Okay, then now similarly, here the angle is d theta. D theta. So that means in order to get the length of this line segment, you need the radius, namely the length of this line segment here. Here. But that's no rho, but that's, oops, that's actually r. But r was rho sine phi. So therefore, the volume factor here, the volume of this little thing, tiny volume element, so to speak, that is rho times d phi times d rho times rho sine phi d theta. So remember, this length of this is rho sine phi d theta. And if you simplify this, you get rho squared sine phi d rho d theta d phi. So that's why we need the factor rho squared sine phi. However, if you didn't really understand this rationale here, maybe okay, just know that if you use spherical coordinates, you need this extra factor rho squared times sine phi. All right, so that's the end of this video. And in the next video, I'm going to work out a couple more problems by using spherical coordinates.